Well, good evening, everyone. It's good to be back with you again. It seems like it's been forever. We had to pause our classes due to hurricane and internet problems, but we're back now. I know we recommended people try to test in December when we thought we'd be finished with the class. Some people have and have let us know, and that's really wonderful. For those of you that are back with us, thank you so much for hanging in there. We're excited to finish up the series. I've got chapter 10 tonight, so this will be my last time in the box for this series. Gary will be up next week to talk about chapter 11, which is safety, and then we'll be doing a practice test at the same time. For those who are finding us online, if we don't know that you're out there, please let us know. And for everyone, we definitely want to know how you did when you go to test. So that's a big encouragement to us. So with that, we're going to go ahead and jump right into it. Tonight's chapter 10, Topics in Radio Propagation. And there's a whole bunch of mini topics here. And I've tried to make an extra effort to make some of this practical. They jump around a lot in the pool questions. Some of it is really helpful going forward in your ham radio endeavors, and we'll try to point those out. So we're going to be doing 4 sections tonight. We're going to start out with section 4.1, the electromagnetic waves. This is a pretty easy one. And I had to kind of smile because Kessler's video said there was only 1 question in this section, but there's actually 4, so apparently he hasn't updated everything yet. I always like it when we can outsmart him because he's pretty smart. All right, so electromagnetic waves and fields. And this occurs when energy is released in the form of radio waves, potential energy in the form of batteries or whatever. When we generate RF, an electric and magnetic field results. So the changing fields create the waves that can propagate through space. That's magic, the magic of radio waves. And then those radio waves tickle electrons in an antenna and create electric waves in the antenna, generating a very weak current. And then from the radio waves being sent, I can hear you. So in terms of being associated with antennas, there's a couple pool questions here. Again, I'll remind you, blue text represents a pool question, so you'll need to know these things. The diagram at the bottom looks a little bit confusing, but if you look at this part of it, it makes it a little bit easier. This is the direction of the radio wave, and this is the electric field in this case, and the magnetic field. When the antenna is oriented vertically, this is the result of what we have. So the 2 things we need to know: the direction of the electromagnetic field. It travels at right angles to the electric and magnetic fields. Those 2 fields go together, no separating them. And the orientation of the wave components, the component fields of the electromagnetic wave are at right angles to each other. And I've got an animation here if it works. I got to turn off my pointer first though. I don't think this will work. Okay. Here we go. I couldn't get down to the screen. All right, now we'll try it. So here you see the E field and the...
We're not seeing it.
Okay, it's showing up on... Oh, you know why? I think I have to drag it over. There we go. Yeah. So you can see the E field is the one that's vertical. It's a little bit easier to see here in the animation. And the wave is going out. That's the x-axis. So this is a vertically polarized signal. And if we flipped it 90 degrees, it would be horizontal. So that may be helpful there. All right, so what about the speed of electromagnetic waves? Well, most of us think that they travel at the speed of light. That's pretty much true. And the speed of electromagnetic waves in air is real close to the speed in space. But it depends upon the density of the medium that it's traveling through. You've all seen this picture. Again, I need to turn on my pointer. Seen this picture? We put a pencil in a glass of water, and it looks bent. That's because the refraction, the light speed changes depending on the medium that it's traveling through, and water is a different medium than air. And in the case of radio waves, of course we talked about air. The ionospheric layers, D, E, and F layers, all have a different density of electron flux. So they will bend radio waves. The speed in space, and then in Earth and soil has a different speed yet. And all of these things are important because they have to do with the refraction of the electromagnetic waves. So waves appear to bend at media boundaries. That's because of the speed change. It's due to refraction. And the degree of speed change is reference to what's called the index of refraction as compared to a vacuum, or speed in space. Finally some blue text. Thus, the index of refraction determines the speed of an electromagnetic wave in a medium, and it will be different depending upon the medium. When it changes medium, that's when the wave will refract or bend. So there's a practical application. The velocity factor, I think Gary talked about this when we were talking about antennas. The speed of RF in coaxial cable is different than the speed of RF in air. And that has to do with cutting the right lengths if you're going to be making tuned stubs and so forth. So we need to know that. But that's why it's different. So polarization, we've got several different flavors. As I mentioned before, it refers to the orientation of the electric field with respect to Earth. Spinning satellites create a special case for us. They create circularly polarized waves, and we can simulate that on ground by the way we connect an antenna. So circularly polarized electromagnetic waves are waves with a rotating electric and magnetic field. And there are ways that we can simulate that in our antenna to pick that up. But it can be a little tricky because you've got right hand and left hand polarized waves, and the antenna's got to be set up accordingly. So we'll see if I can make this work again. So here's an antenna with here we go. The vertical polarization, got the electric field vertical, horizontal is here, and then we've got right and left hand circular polarization. Right into some poll questions. This is the easiest section tonight. So in what direction does an electromagnetic wave travel? So you can unmute and give us an answer phonetically.
Delta.
It is delta. Travels at right angles to the electric and magnetic fields. It's going away from the antenna. How are the component fields of an electromagnetic wave oriented?
Charlie.
Charlie, they are at right angles. And that's always true. You can't have an electromagnetic wave unless you have both elements there. What determines the speed of an electromagnetic wave through a medium?
Delta.
It is delta, the index of refraction. Very good. And then what are circularly polarized electromagnetic waves?
Baker?
Yep, Baker or Bravo, waves with rotating electric and magnetic fields. If you've got a right-hand polarized antenna and you're trying to receive a left-hand polarized signal, you might not hear anything at all. All right, right on into solar effects, our next section. So if you're taking notes, you might want to write down some of these slide numbers, because I'm going to recommend a couple of videos here. And all of these links will be working when Gary publishes the PDF tomorrow morning. But rather than have to search through the whole slide deck, if you're interested in some of these, you might just want to jot down. This is slide number 12. And this NASA solar cycle video is fabulous. They really, really do a good job. And then this site is a playlist. It has a whole bunch of videos regarding sun effects. So if you're interested in knowing more, I highly recommend those. So our sunspot cycle is 11 years, and we're approaching the peak now, which is very good news. Great for DX. So the sun is a really complicated planet. It's not a planet, it's a sun, right? Okay, so all kinds of crazy things go on. We've got flares happening, we've got coronal mass injections, we've got solar wind coming off the sun, just all kinds of things. It's a continuous thermonuclear fusion reaction going on. And the part of the sun that we can see is referred to as the Earth-facing disk. The UV radiation and X-rays that come off the sun are called ionizing radiation, because they're strong enough to actually knock electrons off the atoms in our upper atmosphere, ionizing the ionosphere. Then we've got the solar wind, which is the continuous flow of charged particles from the sun. So that's coming at us all the time. And then there's eruptions that occur, like the solar flares and the coronal mass injections that can wreak havoc. So here we got a picture of the Earth's magnetic field. And the thing that's interesting about this is there's a difference between the geographic North Pole and the magnetic North Pole by just a few degrees. So the Earth looks like one giant magnet, in this case a bar magnet. And this is significant because the charged particles from the sun are attracted to the poles. They can enter our magnetosphere through the north and south poles. So if you use a magnetic compass when you're hiking or hunting or whatever to find your way out of the woods, if you get lost, most compasses will actually have an adjustment on them called a declination adjustment, where you can figure out what the error is between true north and magnetic north, and then have your compass direct you the right way. Since it's just a few degrees, it usually isn't tremendously significant. So here's a picture. If you've ever been to a shopping mall, a lot of times you'll come up to a sign and it'll show you the whole layout with a little arrow that says, "You are here." Well, this is us. In this case, this is the Earth. And what we're looking at here is the magnetosphere surrounding the Earth. The Earth's magnetic field shields us from the solar wind, which is particles and junk that come flying off the sun. And of course, the magnetic poles, as I mentioned, is a place where that magnetic energy contained in the solar wind can actually enter the Earth's magnetosphere. It's like iron filings on paper with a magnet underneath. You've probably all seen that in science class when you were in grade school, if you can remember that far back. So a little bit more on the effect of charged particles. Here we've got our electromagnet, which is, or not we've got basically a bar magnet representing the Earth. And if we had iron filings, they would be attracted to that magnet. And we've got the law of attraction and repulsion. We've got a south pole and a north pole. They'll attract. And if we've got like poles facing each other, they'll repel. That concept will be important when we consider charged particles from the sun. There's a solar parameter called BZ, or B sub Z, that tells us what the orientation of the particles coming from the sun happens to be with relation to the Earth. BZ. So there's all kinds of parameters having to do with the sun. Solar data, we'll call those collectively. So BZ is the first one that we're talking about. There's other flavors of B as well. But BZ is important because it will tell us whether or not the solar wind, particles from the sun, the junk that's being thrown off by the sun, will be able to enter our magnetosphere. Now, wouldn't it be nice if we had a satellite between the Earth and the sun for advance warning when something was going to be coming? Well, the particles from the sun travel at different speeds. If we're talking solar wind, those take days, hours to days to get to us. So we do have some advance warning. And over here, we have a picture of a satellite that happens to be either on the side or behind the sun, or behind the Earth rather, that can give us a little advance warning of what's coming to us. Something called the ACE satellite, which measures solar wind. And there's magnetometer satellites that measure magnetism. There's Aurora cameras and images. But anything coming to us from the sun that is in the form of light is way too fast, because we don't get any advance warning because we don't have anything faster than the speed of light. Those are things like flares, yeah, you have solar flares. Thank you, Gary. Those come at the speed of light. So when those happen, we have no warning. So here's some solar data that affects propagation. We'll be talking about some of these things. This is one that I picked up from April of 2019. I think I probably got it off the internet someplace. We need to mute all again there, Gary. So we'll be talking about this. In this case, solar flux index, SFI, is 67. Sunspot number is 0. This is very sad. That's a very, very poor propagation, and we have suffered through the minimum of the solar cycle, the 11-year cycle. We're close to the peak now. And then here's one from December of 2024 over here. And here we see that the solar flux index is 167, or 161. Sunspot number is 114. And this one I've marked as very happy. This is a good indication of DX, long distance communication. Doesn't mean that things are going to be completely rosy, because there's something called the A and the K index that we'll get to in a minute, and they represent a geomagnetic disruption. So even with sunspot numbers being good in SFI, we still might not have good conditions. More about that to come. Now, how can you get to this? You've probably all seen this image and maybe had questions about it. There's a lot of stuff here, and I'm going to give you some resources. There's some links to some resources that explain all of this. Some of these things are very useful to know about, and some of them are just interesting, put it that way. But if you go to the QRZ homepage, qrz.com, they will have a version of this there. You can go directly to Paul Herman's site. He's the author of this and a whole bunch of other stuff that are related. You can go to his site directly. So these are a little bit dated, but I'm just showing them for illustration. So you can get some idea what's going to be going on in terms of propagation, or if you're like me, sometimes you just go to the band and listen. And sometimes a band is actually open, but it's quiet. You turn around, there aren't any signals there. But you may be amazed if you call CQ, you'll get people from all over the place answering your call. So sometimes the band is open, even if it's not active at the time. Another trick that's useful is to listen to FT8 frequencies because they're on every band, and FT8 is probably the most used mode that we have. And if you can hear a lot of activity on the FT8 frequencies, that probably indicates that that band is open to some place in the world. So here's diving into this just a little bit more. The a solar flux of over 150 is ideal for propagation. So in this case, the SFI number is 167. And here's some relative values there. Sunspot number is related. These are related to each other. And again, some values to tell you what's good and what's bad. When I look at this, usually if we've got SFI and sunspots in triple digits, that's potential happiness. If you're chasing DX or working an international contest. So there's a couple of resources here, a beginner's guide and a glossary from the author of this resource that go into great detail to talk about this. The beginner's guide, the person that put this together, VE2XIP, couldn't find anything on the internet that comprehensively described all of this stuff, so he decided to write one. So it's a beginner's guide. So let's take a look. I grabbed today's solar numbers just for the fun of it. These aren't quite as good as the ones that I listed from December. These get updated every couple of hours, so if you have a link to this information, it's really current. So in my case, I downloaded an app. I use an Android. It's called Band Conditions. I don't see that app listed in the Play Store anymore, but there's a whole bunch of ham radio apps in the Play Store, and I'm sure that several of those will display this data. So I look at this just about every time I operate. When I turn on my radio, I'm curious to see what my chances are going to be. That is just something that I like to do. So SFI and SN in triple digits shows the prospect of great DX conditions. And then the one I haven't talked about yet, the K index, that's over here. In this case, it's 3. A K index less than 2 is also a good sign, and it correlates to an inactive geomagnetic field. If K is high, that means that the magnetosphere is disturbed, and even with good sunspot numbers, propagation might not be good. So just some ways that I use it. So back to BZ, measures the direction and strength of the interplanetary magnetic field. And here's remember our magnets and iron filings. Well, the wind, the solar wind, is like the iron filings, and the Earth is like the magnet. When BZ, the value of BZ, that parameter goes negative, the solar wind strongly couples to the Earth's magnetosphere. That has a definite effect on propagation. So you can think of BZ as a door that allows transferring of significant amounts of energy from the sun into our system here. And the more negative it goes, the more energy that can be transferred. So here's our bar magnet, the Earth, and all of this stuff coming at us is the solar wind. So some measurements. So solar wind adds to the Earth's geomagnetic field. The Earth has a geomagnetic field by virtue of being a magnet itself, but that magnetic field is disturbed when we add charged particles from the sun. All right, finally some blue text. So BZ represents the north-south strength of the interplanetary magnetic field. Okay, meaning what we're getting from the sun, the solar wind and the particles. If BZ is negative, then it aligns north to south like the Earth's magnetic field. This southward orientation increases the likelihood that charged particles from the sun will cause disturbed conditions, which in terms of propagation happiness, anytime we've got something disturbed, we're disturbed, okay? Disturbed usually means bad. So a few more measurements. The K-index ranges from 0 to 9, and it measures the disruption to the geomagnetic field, measures the short-term stability. The A-index is derived from K, and it has a different range. It's averaged over a longer term, over 24 hours, actually. And K is the only one that I really care about because I want to know what's going on right now. I don't care about the average over the last day. I want to know what's happening now. So that's the one that I look at.
Just under 3 right now.
Okay, so right now that's good. And it's been above that. We've had disturbed conditions for the past several days. But today it's coming down again. This ebbs and flows. So a rising A or K index indicates an increasing disruption of the geomagnetic field. And of course that disruption will affect our propagation in a negative way. I always look for low K. So the G index is measuring geomagnetic storminess. It ranges from 0 to 5, and it's based on A and K. A lot of these things are related. We've got a few more measurements here. We've got something called the 304A parameter, and then measurements for flares and geomagnetic storms. The 304A parameter measures UV emissions at 304 angstroms, which correlates to the solar flux index. The advantage of this parameter is that when we can't see the sun, we can't see the sunspots because of the overcast sky, 304A does have a relationship to that activity. And this is a fairly easy pool question because the 304A solar parameter and 304 angstroms, well, the question and the answer, the 304 line up, so that'll be easy for you. Now, flare intensity, okay? So those change, A, B, C, M, and X. The higher numbers or higher letters are increased intensity. Greatest solar flare intensity is X. And the cause of short-term radio blackouts is solar flares. And I think you mentioned, Gary, that we're in a radio blackout right now?
Okay, earlier, yes, we were. There was an A-class solar flare. It was not major, it was minor.
Okay, yeah, so A is the lowest one on the scale here. So, and do you have a site that you look at to see that?
I have an app on my phone, the iOS app for Apple. It's called Space Weather.
Okay. All right. I know that there's several that are out there that you can kind of tell what's going on in terms of flares and geomagnetic storms, in addition to what we showed from Paul Herman. So geomagnetic storms, these are generally bad. G index, it's a different index than these. That goes from 0 through 5. In the space weather term, G5 means an extreme geomagnetic storm. So if you have a resource that will give you these numbers, which I believe the Paul Herman one does that I showed you, that means that if you wonder why all of the bands are dead and you can't talk to anybody and you're worried that your antenna might be laying on the ground, well, it might be because we're in a geomagnetic, extreme geomagnetic storm. The worst time for this to happen is right before a contest, by the way.
And unfortunately, it has happened to me.
Uh-huh. Yep.
I thought, did my antenna wire come off? What?
Yeah, things just go dead. Doesn't happen very often. So here's a video that kind of shows the activity of the sun. And hopefully this will show up for you all. That's going out. Kind of watch, here's our sun doing this. Ooh, there's a flare or a mass injection. Guess what? It's coming toward the Earth. Here's the Earth. It slams into us. And you can see that it kind of disrupts the magnetic field around the Earth. That's a good visualization. There's some great references on solar. I listed a bunch of them here. This one here is excellent. I like it when books are available in Kindle because not only are they a lot cheaper, I'm told that Amazon offers a great deal to authors if they can keep their Kindle price under 10 bucks. That's why you see so many at $9.99. But this is a book worth having if you're interested at all in propagation. The ARRL handbook is excellent. And I met the guy that rewrote the entire propagation section of the ARRL handbook about a year ago at Contest University. So I had to buy that version of the handbook because his presentation was fabulous. Spaceweather.com. There's a bunch of other ones here, NOAA, NASA. And then if you watched the Kassler videos, he gave a number of interactive presentations that showed some of these effects, and that was from dxatlas.com. One thing that I like to do, I program the FT8 frequencies into my radio so I can very quickly scan through them. So we got 160 through 6 meters. And if I hear activity on these frequencies, I know that the band is going to be open someplace because there's more people on the FT8 frequencies than just about any place else on the band. And if you're actually set up to decode FT8 using the WSJTX software, you can actually tell where the band is open. So if you see that there's tremendous activity going on 40 meters, and Europe, all kinds of European stations are showing up, you'll know that if you want to do sideband or CW, you're going to have a pretty good chance. So this is a quick and easy indicator. Some people just spin their VFO up and down the band to see if there's any signals there, if they don't do any of this fancy stuff. And then I met Tamitha at Himvention a couple years ago. She was there. She's normally there doing a presentation of some kind. She's called the Space Weather Woman, and she's amazing. If you listen to a weather forecast on the TV this morning, they tell you everything that's going on here on Earth. Well, you get the equivalent of that in terms of what's going on in space through her forecasts. And I just uploaded, or I updated this link today. This was current as of December 19th. She tells you what's going on with happening within the sun and all of the interrelationships to us and even propagation sometimes. She also has a YouTube channel and a website. But this video is really worth watching. If you've never seen her, I'd highly recommend it. This is slide number 29 if you want to make a note of that. Don't have to look for it. So into some questions. What is the cause of short-term radio blackouts?
D.
Solar flares, yep. Thank you. Yeah, I can't tell the difference between B and D, so delta does it for me. Which of the following indicates the greatest solar flare intensity?
Delta.
That's X, exactly. It happens to be the highest letter in the answers. Which of the following is the space weather term for an extreme magnetic storm? Delta, yeah. Remember, G is the parameter that talks about geomagnetic storms, and 5 is the worst of the worst. What does the 304A solar parameter measure?
Bravo.
Yep. I thought somebody said waffle there, but no. The UV emissions at 304 angstroms correlated to the solar flux index. And I just noticed something. I said that 304 appears in the question and the answer. Well, I see in this version of the pool questions, they've got another 304 here, so my little trick won't necessarily work. But as long as you can remember that it is, that this answer, UV emissions, correlated to the solar flux index, you'll have
But
that
angstroms is actually a measure of wavelength. It's
Exactly.
a unit of measure for wavelength. So.
Yep. So it'd be listening at a specific frequency would be another way to say that. And I think it's 10.7 gigahertz or something like that. What is indicated by a rising A index or K index?
Alpha.
Alpha, increasing disturbance of the geomagnetic field. You want the K index to be low. What does the value of B or B sub Z represent?
Charlie.
It is Charlie, north-south strength of the interplanetary magnetic field, or it's the way that the particles from the sun are being are aligned relative to the Earth. What orientation of BZs increases the likelihood that charged particles from the sun will cause disturbed conditions?
Alpha.
It is alpha, that's southward. Yep. Good, we're doing great here for time. So we're going to get into HF propagation. This has got a lot of practical stuff in it. So radio waves can typically get from A to B in 3 different ways. We've got what's called space wave, which goes up into the ionosphere, comes down again. We've got point to point. Transmit and receive antennas can see each other. And ground wave signals travel along the Earth's surface. It's down here. So space wave, point to point, and ground wave. Oh, sky wave is the one actually that goes up the ionosphere. Signals will go up into the sky and return to Earth after refraction from the layers in the upper ionosphere, also called skip. So up, and then skip back down. All right. So ground wave and sky wave propagation, there's a couple of things that we can pick up from this diagram. These are called angles of incidence here. It's the angle relative to the Earth that we're sending the signal up. Of course, if you've got a directional antenna, a beam antenna, you might be able to affect that somewhat. So the angle of radiation, also the design of the antenna, different antennas have different angles of radiation. In this case, we've got an angle that's going up, and it's not refracted enough to bend back down to Earth, so it just goes off into space. Here's another angle. It's coming down over here. Now notice this is a shallower angle, a lower angle, and because it hits the ionosphere at a further point, it comes down at a further point on the Earth, kind of like cue balls on a pool table. Of course, they qualify this rough generalization. The real world is much more complex than this. Yeah, absolutely. Another thing that we can see from this diagram is something called the skip zone. Now, I mentioned that we had ground wave, and signals can propagate a certain distance from an antenna via ground wave, and I'll have a diagram of that coming up. So any place in this area, we'd be able to talk to somebody. And via skip here, we can talk to somebody over here. But in between, there's no RF path between the end of ground wave and where the skip comes down. And this is called the skip zone, which is kind of a dead zone. So we get 2 different kinds of single hop jumps that are shown to us here. So in the skip zone, I cannot hear you. Another concept here, something called the critical angle. That's an angle that you shoot up where it's just high enough where it will come back down again. Whether it refracts or not is referred to as the critical angle. Beyond that, it'll go off into space. Interesting story for me, I was working on getting Workdal states, and 20 meters for me was, Georgia was one of the states. I live in South Carolina, and Georgia was one of the last states that I needed for Workdal states, and I couldn't get it. And the problem was it was too far for ground wave, and skip would go right over, right over Georgia. So it took me quite a while before I found the perfect conditions so that I could actually get a signal from Georgia and get my award. So depending upon where you want to work, you've got to pick frequencies and strategies, you know, what bands are open and where they're open to, what the propagation is doing to pick those up. And there's tricks and techniques you can use. So here's just a different image of showing HF propagation. We've got the ionosphere, we've got ground wave, we've got the sky wave, we've got, in this case, we're hopping twice, come back down again. In this case, they're showing an AM radio transmitter, but this would be true of any band. Now, believe it or not, you can actually go all the way around the world this way. You just keep skipping and skipping and skipping. Maybe not on AM radio frequencies, but on some of our ham.
Yeah.
Okay. Yeah, I've not seen that on the AM broadcast band, but Gary says it's possible. And being a broadcast guy, he would know. So ground wave, let's talk a little bit about this. Ground diffraction with vertical HF antennas, first of all. So in the case of ground wave, this is where we're hugging the Earth, the lower part of the radio wave loses energy because of currents induced in the ground are mostly absorbed, limits distance. This slows the lower portion of the wave, causing the wave to tilt forward slightly because the index of refraction in soil is different than it is in air, causing ground wave to follow the curvature of the Earth. So the maximum range of ground wave propagation will decrease as the signal frequency increases. So at 28 megahertz, via ground wave, you might only make a couple miles. Ground wave, though, can be effective on 160 and 80. So the key thing to remember is this is an inverse relationship. The range is inverse of frequency. Maximum range of ground wave propagation decreases as the signal frequency increases. Or another way to think of that is 160 and 80 are ground wave bands, or can be good ground wave bands. So here's a real interesting chart. I actually stole this from Kessler. He did give us permission to use his images. And what we're seeing here, here's 80 meters, 40, 30, all the way out to 10. And here's some distances, or some frequencies. The frequencies are across the bottom. Distances are going up here. So 10 meters is only going a few miles. 80 is, in this diagram, is showing out to 60. So this graph is kind of, it illustrates what we talked about in the previous slide. So some key points, a couple of pool questions here. Vertical polarization is supported by ground wave propagation. And a good way to think of that is that here's a picture of an AM broadcast station, multiple towers. They're all vertical, notice. They actually load the towers. So vertical polarization is supported by ground wave propagation. In fact, only vertical polarization works for ground wave. So it's effective only on the lower bands. And the maximum range of ground wave propagation decreases as the signal frequency increases, making 10 meters pretty dismal via ground wave. Talk a little bit about the ionosphere. We cover a lot of this in the general portion, or the general class, which we've got one coming up in February. The extra class that we're doing during this series just expands on some of those concepts a little bit more. So you'll probably remember that we've got 4 regions, as they're called, of ionization. And I'm going to show you, I think at the end, I've got some bonus material that describes how they figure these out, how they can actually measure them. Here's the Earth, and these are the different regions. This is massively not to scale. It's just shown this way for clarity. The layers or the regions are much, much closer to the Earth, actually. That's just for review. So for HF propagation, skip comes to play here. This shows some where the airplanes fly. I don't think for HF propagation you'd be using dish antennas, so whoever created this diagram didn't know much about radio, but they got the concept right. So here's point to point, and of course, skip. And then space wave here, point to point. So there's something that, there's no pool questions about this, but it's something useful to know about. It's called NVIS, some people call it NIVIS, Near Vertical Incidence Skywave Propagation. That's where you, let's say that you live in a mountainous area like Dave Kessler does, and it's difficult to make contacts with people on the other side of the mountain. But if you can send a signal, the red rooftop is where you're transmitting from, if you can send a signal almost straight up, you can come down on the other side of that mountain that you couldn't communicate through. So this is a strategy used by the military and by hams in Arizona to make contacts when they otherwise couldn't. So that's called near vertical incidence skywave propagation. The way that you can make your signal go almost straight up is to have a dipole very close to the ground, like 1/10 of a wavelength or something like that. Most of the energy is going to be going straight up. So in this case, oops, too far away. But these closer in ones, we can definitely communicate with these locations. The antennas that shoot straight up into the air, you may have heard of this term, they're called cloud burners because most of the energy goes straight up or close to straight up. So a little bit more on skywave. Signals travel into the ionosphere, can be refracted or bent by ionized gas in the ionosphere, the E and F region, returning to Earth some distance away. And the reason that they're bent is because the electron density is different in these different layers. It occurs because the region of ionized gas causes the radio wave to slow down, which bends the wave. It's a denser or less dense medium, actually, as you continue going higher. So refraction or skywave is the primary HF mode of long-distance propagation. So of the layers or regions we've talked about, the F layer can hop about 2,500 miles. It's approximately from South Carolina to California. One hop, the skip distance for the E layer, so the next layer down, is about 1,500 miles. Just background and context. These used to be pool questions, but it's still good context. Now here's this one might seem a little tricky, but think about it. Lowering a signal's transmitted elevation angle increases the distance covered by each hop. Well, let's look up here to see if we can make sense of that. So this is a fairly low angle of radiation compared to this one. You can see if we have a lower angle of radiation, it goes further. So hopefully those two things will connect, so this will make sense. Lowering a signal's transmitted elevation angle increases the distance covered by each hop. We see that graphically up here. Now, there's some really freaky things that happen in the ionosphere. One of those effects creates what's called ordinary and extraordinary waves. So here we've got the ionosphere, and this is a linear polarized, this is Gaussian wave, but it's linearly, easy for you to say. Yeah. So this might be horizontal polarization or vertical. When it hits the ionosphere, though, we split into two different waves called the ordinary and extraordinary. And these things can take off in different directions. I don't know if you've ever heard of the concept of one-way propagation. Well, this might be coming down in a different part of the world than this is. So somebody out there can hear you, but you can't hear them coming back, or vice versa. So that splits into an extraordinary and an ordinary beam, as they're called. Very freaky stuff. And another thing that means is if somebody is transmitting with horizontal polarization. There's a good chance that somebody with a vertical antenna over on this other side is going to be able to hear you. So that's a good thing. So those are some concepts, and this is actually called elliptical polarization when they split here. And the concept of elliptical polarization, interesting factoid, was introduced by Augustin Jean Fresnel in 1882. We're going to be talking about Fresnel zones in a little bit. And again, we've got a number of scientists from the 1800s that came up with concepts about radio waves that couldn't be proven because we didn't know how to do radio waves back then. So I found that interesting. Another interesting factoid in Alaska, sometimes the hams, this was a comment from Eric Nichols, who lives at the North Pole, Alaska, which is a town. Alaska is very strange in terms of the magnetosphere above it, so they never know where to point their beams in terms of what's going to result from all of this. So the ordinary and extraordinary waves are independently propagating elliptically polarized waves created in the ionosphere. That's what happens here. They split into those two flavors of waves called elliptically polarized. Some people will say that you send it up horizontal, it comes down horizontal and vertical. That's pretty close to the truth too. These waves may take different paths through the ionosphere, exclamation point. You would think that they'd go the same place, but they don't necessarily do that. So they might be coming down in places where one person can hear and you can't hear the answer coming back. Chordal hop is another interesting concept. Here we've got some regions of the ionosphere shown, and here we've got the F layer. You can't really read the stuff in the middle here, but suffice it to say that when a signal gets up to this layer, it may bounce back and forth a couple times, or a whole bunch of times, before it comes back down again. And that's what's called chordal hop. So it's successive ionospheric refractions without an intermediate reflection from the ground. So the kind of skip that we would be expecting would be something that would go up and come back down to the Earth again. A chordal hop, you can go a long, long distance without ever coming back down to the Earth. So the signal may be a lot stronger when it does come down because it hasn't expended so much of its energy hopping up and down. More efficient because the waves don't have to return to Earth and can travel a long distance before being refracted back to Earth. Just a concept. You won't see it very often. It was actually hams that discovered this, by the way. Hams have discovered so much in terms of propagation technology and physics. It's just amazing. And we're called amateurs, right? Like we don't know what we're doing. Well, we've really advanced the science in a lot of these areas. Now, the effect of chordal hop is that the signal experiences less loss compared to multi-hop using Earth as a reflector. So this might sound kind of similar to this, and it is, but it's two different pool questions. So I wanted to put the text of both of them in. So I have an enlarged picture here on the next slide. We haven't talked about sporadic E yet, but there's a mysterious cloud of electrons sometimes that forms in the E layer that will reflect signals, called sporadic E. Lets you talk to places that normally you couldn't with other types of hop. So I see they've done some kind of cute things here. Let's trace the green one. Green one goes up to the F layer, comes down to Earth, goes up to the sporadic E, back down, all the way up and then back down. So that's 1F plus 1E plus 2F, the number of hops that it made through the various layers. And here we've got our chordal hop going on up here again. We'll be talking about sporadic E a little bit more coming up too. So how does this affect propagation, you're wondering? Well, again, some more little bits and pieces that are good to know and sometimes are pool questions related. So polar paths, a polar path is a path that you shoot over the North Pole for us here in the United States. Polar paths are more likely to experience high levels of absorption when the A or K index is elevated. Remember, that's showing us that we've got a disturbed magnetosphere, and we've got particles coming in, and those are going to be attracted at the poles. So that's why we have a higher level of absorption at the poles. Now here, I put these both in because the way they wrote the pool question this time is a little bit more confusing than this explanation. Signal paths through what they call the auroral oval, that means over the pole, are likely to experience high levels of absorption when the A or K indices are elevated. Same thing said two different ways, just you need to know that the auroral oval happens to be the North or South Pole. Okay, here's another random fact. A sudden rise in background noise across a large portion of the radio spectrum is an indication that a coronal mass injection or a solar flare has occurred. So here we've got the sun, and it can do all of these crazy things. And I think Gary had mentioned in a previous class that the absence of a signal could be perceived as an increase in noise. Of course, the absence of a signal would be a result of a RF blackout due to a flare or a CME. A little bit more about skywave or skip. I'm going to talk about long path and short path. Here we've got the Earth, we've got the daylight side, we've got the night side here, and we've got stations, and you can't read the calls, but we've got stations at each of these locations that are wanting to talk to each other. Now it's good to remember that the circumference of the Earth is 25,000 miles. That means if you started walking here and you could walk on water, and you went all the way around the Earth and wound up back to where you started, that'd be 25,000 miles. So the short path, if we pick a spot here, halfway around is going to be 12,500 miles. So the short path is going to have to be less than 12,500. The long path would be going around the other way, and it would be more than 12,500. This is going to come up again when we look at Earth-Moon-Earth propagation. So just kind of remember the 12,500 number. So long path would be 25,000 minus the short path distance, because all the way around would be the 25K. Here's an example. Tokyo to Pittsburgh, 6,600 miles at a certain angle or compass bearing. Long path would be 18,000 miles at the opposite bearing. You rotate 180 degrees around, so 328 minus 180 is 148, just the complete opposite bearing. So that's two ways of talking from Tokyo to Pittsburgh. Yeah, this does actually happen. Sometimes you will not be able to hear a station. Maybe you've got a schedule set up with somebody that you want to talk about. Let's meet at a certain time, and can't hear them. Now, you've got a story, Gary, of somebody that you worked that way.
Well, I was just going to say that if you look at the spotting sites, many times they will put a little notation that will say long path or LP. Mm-hmm. That's a clue for you to know which way to point your antenna. And even with my 2-element hex beam, it makes a real difference between inaudibility and audibility. Yep. But yeah, my story was back with my friend Greg Surma, K8GL. He was on a de-expedition to Montserrat. And so we had a schedule set up. I was going to call him from Michigan. And so I was calling from Michigan down to Montserrat in the Caribbean, had my antenna pointed in that direction, nothing, no signal, no signal. On a whim, I turned it 180 degrees and called him, and there he was. So even when you don't know it's going to work, it sometimes works.
Yep. Very, very cool. You wouldn't think that that could happen, but you can actually bounce. Of course, in the first case, Gary was in the skip zone. The second case, he was not in the skip zone. It came down where it needed to go. So another interesting fact is that it takes about 1/7 of a second for a radio signal to go all the way around the Earth. So if you notice an echo on a signal, you could try to turn your antenna beam 180 degrees for a long path. So that's another interesting thing. I had a friend, he and his wife were both hams, and he was kidding his wife that if it took a long time for his message to get to her, it's because he was sending a long path. Of course, in the same house, that wouldn't happen. An echo on a received signal may be caused by receiving a signal by more than one path or going all the way around the Earth. I don't know if you've ever heard of LDEs, long delayed echoes. They're real spooky things where signals come back that are way longer than that. And it's kind of, I don't know if you'd call it paranormal or whatever. And have you had any experience with that, Gary? No.
I'm not saying it's aliens, but it's aliens.
Okay, very good. Long delayed echoes. But we won't see that in the test because it's sort of a paranormal thing. So I mentioned 25,000 miles at the speed of light winds up to being about 150 milliseconds, a 1/7 of a second. And humans can discern a difference as low as 30 milliseconds. So this echo effect is clearly discernible if it exists. You won't see it very often. It's just kind of all side information to keep you entertained, so to speak. So gray line we're going to talk about next. Here we've got Mr. Sun, or Mrs. Sun, shining on the Earth. Here's the North Pole, the South Pole. This is the daytime side and the nighttime side. Well, where the daytime and the nighttime side meet is called the gray line. So it's partially sun, it's partially day, and it's partially night. And some real magic things can happen propagation-wise if you've got two stations and they're both on the gray line. So the day side has an ionized F2 layer. The night side is just coming into sunlight, has not had time to ionize, and it will and absorb the lower frequencies. So the double benefit of lower frequency propagation, and this happens at dusk and dawn. And the best time, in my case, the best time to work Asia would be very early in the morning. There's propagation prediction software that will tell you where you are relative to the gray line. And this changes during the seasons of the year too. So here we've got station A, station B. They may be able to have a QSO when they wouldn't otherwise if they're both on the gray line.
And the gray line only lasts about 20 minutes.
Yep, because the Earth is moving. In the Mercator projection of the Earth, will make it look something like this. The reason that you've got this U-shaped thing going on is when you try to make a map of a round Earth, or a spherical Earth, onto flat paper, that this is what results. So this is a gray line.
Anybody else lose Gary or Dad?
Say again? I didn't hear that. Was there a question? Well, I guess not. So here's another image. Kessler had a very, very good demonstration of this. He was using a tool that I mentioned earlier called DS Atlas that you can actually rotate the Earth into different positions and see where the gray line is going to be hitting. So long path and gray line can kind of combine. A few more random facts related to that. So long path propagation is most frequent on the 40 and 20 meter amateur bands. So that's the place you'd be most likely to see it, or the most likely place to try it. I could put it that way. So for shorter distances, the short path is usually the best because the long path is going to be much weaker in signal energy, unless you're in a skip zone, and then the long path could actually be better in this case. So long path is often observed along the gray line or over the nighttime side of the Earth. Here's something you might need to know. A path entirely in darkness is most likely to support long distance propagation on 160. That's because the D region is not ionized when it's dark. And the D region tends to absorb 160. So gray line can be quite effective because the D layer disappears rapidly at night. It's not going to be interfering with those lower frequency signals. So the physics of gray line, again, we see that it's caused by the effect of having one half of the Earth in darkness and one in light, and then the difference between the two being the gray line. Cause of gray line propagation at twilight and sunrise, the D layer absorption is low, while the E and F layer propagation remains high. That's why the magic of gray line works. Another view of the different ionospheric layers during the day. These layers will appear at various heights. At night, they meld, the E layer remains, and the F1 and F2 wind up being just an F layer. And sometimes you're talking to somebody on the air and they're starting to fade out. So that might be because it's getting dark in that part of the world or at your place. So what should be done to continue a ling distance? We'll change that to long distance contact when the maximum usable frequency. We didn't talk about that in the extra class. We discussed it extensively in the general. Maximum usable frequency, you can kind of imagine what that is, highest frequency you can use. So what should be done to continue a long distance contact when the MUF for that path decreases due to darkness? Well, you can switch to a lower frequency band that might still be open, might still have propagation. And that kind of makes sense because when it gets dark, you're going to be losing the ionization above you, but you may still be able to communicate on a lower frequency band. Now, fading is something that most of us experience, and the ionosphere is complex. Well, that is a super major understatement. It is very complex. So, not all energy by station B comes via the same path from station A. Remember, we talked about the ordinary and extraordinary waves. So, because these things can cancel one another due to signals coming via different paths or different reflections, they might be canceling each other, causing fading. And there's a couple of strategies to get around that called diversity reception. There's a couple different kinds of diversity reception. You can have two receivers, have one listening on a vertically polarized antenna, one on a horizontally polarized antenna. So whichever one of these is coming down the strongest, you'll be able to hear them. There's something else called space diversity, where you've got the receive antennas maybe a couple miles apart, and if you have some means of getting the audio back to your main station and a way of voting which one is stronger, that's another way, because one of these might be in the skip zone and the other one not. So that's called space diversity. I don't believe there's any pool questions on that, but this very much relates to what we're talking about in terms of ionospheric propagation. I wanted to share that. Now, propagation prediction, there's a whole bunch of tools that are out there, and some of them are just absolutely excellent. There's tools on websites. I'll be sharing a couple of them with you. And possibly on the exam, you might see amateur radio propagation reporting networks show digital mode and CW signals. All right, well, let's take that apart a little bit. If you're transmitting, let's say, digital mode like FT8, or you're transmitting CW, then the one interesting thing about those modes is that they can be decoded automatically. So if there's somebody in Spain that has a listening station, and that listening station is set up so that they can decode CW, or I'm using FT8 as an example, if they can decode that, they'll say, oh, KE4EA, my friend Dave in South Carolina, just showed up here in Spain. And their automated listening station will take that information and put it on the internet, onto a server. So then it's possible for for you to see where your signal is going in the world. I'll have a diagram of that coming up. Whisper does the same thing, something called the reverse beacon network. But this needs to be digital or CW because there isn't any way for these listening stations to be able to listen to a single sideband station and decode the call sign. So
Not yet.
not yet. Yeah, maybe with AI that might be coming. I don't know. But this is what you need to know for now. So vocab software models HF propagation. As Gary likes to say, these are your tax dollars at work. The U.S. government paid for the development, and I think it was specifically for the Voice of America, wasn't it? Yeah.
That was our whole job, was getting programs into countries via shortwave, and so we needed to know what's the best frequency, the best angle, to which antenna to use. And so over time, our engineering staff put together a lot of statistical information, and they fleshed that out into the VOA CAP program, which we used in-house to determine, okay, we're going to put this Urdu program from the Greece transmitting station at this time, so it's going to go on this antenna on this frequency. This is what told us what to do. And then we had our paid listeners, we called them, our official observers, who would report back to us and say, yes, coming in great, or no, it's not working. So it built up over time to be stronger and better, and the result is with the program that we can use.
Absolutely. And I do a demo in the general class, and I provided the link that will take you to that class. It'll actually show you a demo. The issue that I had, I didn't have Alaska for Parks on the Air. I think that was my case. But I wanted to have Alaska, an Alaska contact for Parks on the Air. So I was wanting to find out what time of the day and what band should I use in order to pick up Alaska. And I demonstrate how you do that and what happens if you change modes, if you change powers in this demo. So you might find that interesting. This link will work when you get it tomorrow. So it's an online program where you can set all kinds of parameters. Showing the gray line here, where you are. Somebody's out in the ocean here. So here's a picture of PSK reporter I took. I jumped on 10 meters and made some FT8 contacts a couple of years ago. And then I went to PSK reporter, and this is the diagram that I got back, showing every place that I was heard in the world. That's a really good way for checking out your antennas. So we'll work through these questions and then take a break. We're going a little bit long in terms of trying to get you out in an hour, but then we'll have the remaining section to do after the break. So how does the maximum range of ground wave propagation change when the signal frequency is increased?
Charlie. Decreases.
Charlie, it decreases. And the way that I remember that is 10 meters is terrible for ground wave. So that fits. What type of polarization is supported by ground wave propagation?
Alpha.
Alpha, it's vertical. You only get ground wave with vertical. What should be done to continue a long distance contact when the maximum usable frequency for that path decreases due to darkness?
Bravo.
Yes, you sounded hesitant there, but switch to a lower.
I was just waiting too long.
Oh, yeah. No, and anybody can jump in, and it's okay if you're wrong, because you'll remember it better if you get it wrong. So no shame. No shame in getting them wrong. Which of the following paths is most likely to support long-distance propagation on 160?
Delta.
Delta, a path entirely in darkness, correct. What effect does lowering the signal's transmitted elevation angle have on ionospheric HF skip propagation? If you decrease the angle, you... What?
Charlie.
Is Charlie, the distance covered by each hop increases. It's like shooting a cue ball further down the edge of a pool table. What is the effect of chordal hop propagation?
Alpha.
This alpha, the signal experiences less loss compared to multi-hop using the Earth as a reflector, so you don't have to come back down to the Earth again. What is chordal hop propagation?
Bravo.
Bravo.
Bravo. Successive ionospheric refractions without an intermediate reflection from the ground. And I read the questions and the answers because some people just listen to the audio. So we were asked to do that for them. What are extraordinary and ordinary waves?
Bravo.
Bravo.
Is Bravo. Independently propagating elliptically polarized waves created in the ionosphere. What you send up isn't necessarily what comes down. What type of data is reported by amateur radio propagation reporting networks?
Delta.
Delta.
Delta, digital mode, and CW, because they can be decoded automatically. What does the VOACAP software model?
Charlie.
Charlie HF propagation. Which of the following signal paths is most likely to experience high levels of absorption when the A index or K index is elevated?
Bravo.
Through the auroral oval, or over the poles. Which of the following is indicated by a sudden rise in radio background noise across a large portion of the radio spectrum?
Bravo.
It is Bravo, a coronal mass injection or solar flare, ejection or solar flare has occurred. On which of the following amateur bands is long path propagation most frequent?
Bravo.
Bravo, yep. 40 and 20. All right, and we're going to finish up the last section after our break. This is the section that has the most pool questions in it, in the chapter actually, but there's a lot of easy stuff here. So at this point, take a break and go do something to get your mind off of this for a few minutes, and we'll be back in 5 minutes. Some stuff that you may not get into for some time, but there are quite a few pool questions, so we won't dwell, we won't spend a lot of time on these individual topics, but there's some very interesting things that happen at these frequencies, like bouncing radio signals off of raindrops, if you could imagine that. You can do that with microwave, actually. So the first question, first topic deals with the radio horizon, and radar operators initially observed this, that sometimes it's possible to hear a signal that's over the horizon. And with VHF, UHF, microwave, normally that's line of sight only. But because of tropospheric bending, shown here, you can actually get a little bit beyond the horizon. So the downward bending is due to density variations in the atmosphere. Again, the refractive properties we talked about earlier. And you just need to know that the VHF, UHF radio horizon is about 15% greater than the geographic horizon. So you can hear a little bit beyond where you think you shouldn't. Now, ground gain and Fresnel zones were introduced in this version of the pool questions. Something that is a little bit esoteric, but we'll mention it and give you enough background, hopefully, to understand why the right answers are the right answers. So ground gain is an increase in signal strength from ground reflections in the environment of the antenna. And in scratching my head about this, I did find one resource, and I'll be sharing the link. In fact, it's down here, Ground Gain in Theory and Practice. The beginning of this article and the end, it's about a 37-page article. The end is a conclusion, and the author comments that the application here is really for a 2-meter moon bounce. If you can, by virtue of what's called ground gain, pick up an extra 6 dB, that can really help you with moon bounce. It has to do with your location, and the concept is that you've got a direct wave shooting toward the horizon, and you've got a reflected wave off the ground. And if this happens to be in a certain area, you can actually pick up some gain by signals being reinforced at the receiving end. So a reflected signal path may arrive from a different direction, and thus path length from the direct signal. To the extent that these signals reinforce each other, they add and result in greater signal strength, which is gain. Ground gain specifically considers the effect of ground reflections combining with the direct wave or line of sight, or LOS. You'll see that term in a manner that will, the signals will add, and you experience what's called that gain, the ground gain. And this is more prominent at 50 megahertz and up. Our book comments on HF as well, but anything that you look at will usually reference something in the 50 megahertz and up range. Good article if you want to dig into it. It's kind of a hairy concept, but if you can just remember the blue text here, that's all you need to know about ground gain. Fresnel zone is something that I was really surprised to see in our book. Normally, this is thought of in terms of radio link design. So we've got a transmitter side and a receiver side, and usually this is maybe microwave. And there's, if you could imagine a football shape or an ellipse between transmit and receive, there's something called Fresnel zones that describe these ovals, these ellipses. And in the first Fresnel zone, anything that makes its way into the zone is going to introduce reflections that will be destructive to the signal received over here. So the trick in designing paths is that you have to, first of all, know what that Fresnel zone is, how big it is, and the distances and the frequencies, and try to make sure you design the path so that nothing gets into that zone. And the rule of thumb, which you can't read here, nearly nasty obstacles must be more than 60% from the center line of the transmit to receive path. That's shown in here. Here's the nasty obstacle. So objects that get in the way of the Fresnel zone can reflect out-of-phase signals, which can cancel part of the signal at the receiver, even if there's a direct line of sight between the antennas. And this seems kind of counterintuitive, because if you've got line of sight between transmit and receive, you ought to be able to talk, right? Well, because of signal cancellation, you could also think of this as multipath, like we see on 2 meters when you're traveling in a car, picket fencing. This multipath destructive interference can actually reduce the signal. So even though the transmitter and receiver can see each other, the signal might be bad on the receive side. And there's some fairly advanced software that will let you calculate all of this. Now the Earth, believe it or not, can be an object that can be an object that infringes on the Fresnel zone. And we have to be able to clear the obstacles out of the Fresnel zone to prevent this destructive interference or loss of signal strength on the receive side. So to do that, there's 2 things you can do. You can either raise the antennas so that the zone clears the obstruction. So in this case up here, if we raised one or both of the antennas so that the building or whatever it is was out of this zone, our problem would be solved. So you either raise the antennas or you have to raise the frequency, because the Fresnel zone becomes smaller and smaller the higher you go in frequency. So the one pool question that we have on this, it asks, it says that the smallest first Fresnel zone will be the highest frequency band listed in the answers in the pool question. 5.8 gigahertz is the highest one. It says first Fresnel zone. So they're actually, the concept here is that within the first zone, anything that impinges on that zone is going to cause destructive interference, out of phase. The second will be in phase, the third will be out of phase, but the one that they're concerned about for path design is just the first Fresnel zone. That's why this word is in the pool question. Now, I went through that at 100 miles an hour. And if you're curious to know more, there is some extremely good information out here. There's a link here that will explain it. This short video down here, cloudrf.video, 2.5 minutes, they actually use the modeling software to show obstacles in the path. Of course, somebody'd have to go out there and survey the site in advance. And then what you can do, what happens graphically if you raise the frequency or raise the antennas to clear that zone. So if you're curious about this and want to know more, some really, really good references here. If you're not curious, which is fine with me, just know that it's the highest frequency band. The smallest Fresnel zone will be the highest frequency band of the options available. Okay, jumping on to tropospheric propaganda. How about tropospheric propagation? Let's do that instead. So troposphere, that's the air that we breathe. That's down here near the Earth. So the normal situation is that heating of the sun, we get hot air on the bottom, cooler air, and cooler air as you go up. You can have something called a temperature inversion where that doesn't occur the same way. So if we get cold air, warm air, cold air, then we have an effect that can actually cause propagation to traverse that as if it were a duct. So weather conditions that create a sharp transition between air layers or ducts in the troposphere can allow VHF radio waves to follow the curvature of the Earth for hundreds or thousands of miles, like a waveguide or duct. Really interesting stuff, and it happens. I'm not much of a VHF guy, so I haven't experienced it personally, but this is real. So here we're showing the propagation duct going through a difference in temperature, air mass, bouncing around there and eventually coming down to the person that you're talking to. And it takes place at the VHF and above frequencies. Just another image. Can go up to 1,000 miles, which is really interesting because you'd never be able to talk 1,000 miles normally between handheld radios or even your base station on VHF. So there's several different kinds of really freaky propagation that can happen at microwave. So atmospheric temperature inversion, we already talked about. That can also create a path for microwave. Occurs along, it often occurs along warm and cold fronts. Atmospheric ducts capable of propagating microwave signals often form over large bodies of water. That's where you'd see these temperature inversions happening typically. And the typical range for tropospheric duct propagation of microwave signals is 100 to 300 miles. Again, that's just mind-blowing. But what we're doing is making a connection between transmit and receiver through this duct. And then rain scatter. You can actually bounce signals off of raindrops if the rain is within the radio range of both stations. Of course, microwave, very short wavelengths. Enough rain, you can actually talk through it. Here's a little bit more on sporadic E. I just introduced that earlier. Here's the E region. Did I have a bigger, thought I had a bigger picture. Yeah, here we go. Bigger picture. Here's the E region. And it's not really well understood why these electron clouds form in the E layer, but when they do, they give you a propagation path that you wouldn't be able to get to via normal F-skip. So occasionally you can get long-distance communication, but because of the fluttery nature of what's received, you can't. It's not particularly well suited to such communication. Normally happens in the 10 meter and up range, 10, 6, and 2. But amazingly, going up to the E layer and back down via sporadic skip, you can get 300 to 1,400 miles in a situation where you shouldn't be able to normally communicate at all. What time of the year can you see this happen? Sporadic E propagation is most likely to occur around the solstices, especially the summer solstice, around June 21st. And interestingly, guess when the big VHF contest is? Well, it's at the end of June.
And field day.
And field day, yep. So Gary is our VHF guy for field day, and he takes advantage of this. So what time of the year can it happen? We talked about it. Time of the day. Sporadic E propagation is most likely to occur between sunrise and sunset. So when the sun is switched on, if you want to put it that way. Here's our picture again. Now, seasonal impact. Now the Earth tends to rotate on its axis through the seasons. We've got December, September, June, March. So sporadic E is most likely to occur around the solstices, especially the summer one, which is over here, end of June. And of course, VHF contests and field day are scheduled at that time. Another strange one, transequatorial propagation, and this was discovered by amateurs. Again, amateurs have advanced the state-of-the-art in communications technology. So in the 1940s, hams were noticing this effect. What is transequatorial propagation, you may be asking? Well, before we get to that, be aware that it occurs on 50 meters, how about 50 megahertz, 144, and to some extent on UHF, and it also happens on HF. Transequatorial propagation is most likely to occur between points separated by 2,000 to 3,000 miles over a path perpendicular to the geomagnetic equator. And I've got a diagram of that coming up. So that's 2,000 miles north, 2,000 miles south, for a total of between 4,000 and 6,000 miles maximum distance. The approximate maximum range using transequatorial propagation is about 5,000 miles. I had a interesting thing happen to me a couple years ago when we were at much worse sunspot, much poorer part of the sunspot cycle. 10 meters had been dead forever, but I kept trying it just to see if there was anything there. And wow, there were signals on 10 meters one day. I think I was doing FT8 at the time, and I must have worked 10 stations. all in Brazil. Okay, well, I'm in South Carolina, and Brazil is on the other side of the magnetic equator, and I'll have a diagram showing why that worked coming up. So the time of day for TE propagation is most likely to occur in the afternoon or early evening. So there's about 3 pool questions relating to transequatorial propagation. Where it occurs, north and south of the magnetic equator, maximum distance, and time of day. In Greenville, South Carolina, is about 2,400 miles from the equator, so that fits within these numbers. And Brazil is about that far south of the magnetic equator, so I'm sure that that's the mechanism by which I was working Brazil stations. So here's a picture. This line across the middle is the geographic equator. This dotted line is the magnetic equator, which is a little bit different. And this red line that I drew in, here's me, and here's Brazil. So I'm within that range. So I'm sure that's what was happening. And it says in the caption down below that it can happen on 28 through 432 megahertz. Of course, I did that on 10 meters.
And this is my secret weapon in the CQ Worldwide contest. Okay. I can always know that on 10 meters in the afternoon on Saturday and Sunday, I'm going to make a lot of signals down to South America just because of TE, because we are in such a great spot for this.
Yep, absolutely. And there are a lot of hams in South America, by the way, for those interested in contesting. Going to jump to auroral propagation. Aurora, think of the poles again, caused by the interaction in the E layer of charged particles from the sun with the Earth's magnetic field. Remember, we talked earlier about how that happens. Severe geomagnetic storms are most likely to result in auroral propagation, because a severe geomagnetic storm would put lots and lots of junk from the sun into the Earth's magnetosphere, and that would tend to absorb signals over the poles. So VHF and above propagation can be up to 1,400 miles via auroral propagation. Again, something you'd never expect. In the northern lights, that's also an effect of the particles that are coming in from the sun. So visible aurora, the northern lights, aurora borealis, it also happens at the South Pole, called the Aurora Australis, at the South Pole. The signals, though, are, because of what they're having to travel through, are usually fluttery and kind of hear a buzz. 2 meter is off, the 2 meter band is often used, and CW is the mode of choice in getting through with that strange propagation mechanism.
I made my first auroral contact this year. There was heavy aurora to the north, so everybody points their antennas to the north. You bounce your signals off of there. It was a sideband contact. It was highly distorted, highly freaky, but I made one.
Where to? Do you remember?
It was Ohio or something like that, but we were both going up to the aurora and then bouncing back down.
Amazing. So CW is the best emission mode for auroral propagation. The sideband will be severely distorted, but Gary was able to do it. So from the lower 48, antenna pointed north will take maximum advantage. I got a diagram of that coming up. It's a picture of some northern lights. Very, very beautiful. They usually don't make it down this far. You usually see them in Wisconsin and Minnesota if they get that far down. Just a picture showing that you point your antennas north, just like Gary did with his friend in Ohio. Jumping to meteor scatter. This is something that I'm wanting to play with, but I don't have a good antenna on 6 meters. But this works because millions of meteoroids enter the Earth's atmosphere almost daily. And they will, when they strike the Earth's atmosphere, a linear ionized region is formed in the E layer of the ionosphere. See, the E layer does some good things for us. So this is where this happens. And the frequency most suited for meteor scatter is between 28 and 148. megahertz. So if you think 6 meters, this is where most people do meteor scatter. You can actually initiate a contact on one side and a different meteor on the other side. So the software has been designed to do that. MSK144 is part of the Joe Taylor suite, WSJTX, and is specifically designed for meteor scatter. So this 15-second time transmission sequences, that's how the MSK144 works. You transmit for 15 seconds and then listen for 15 seconds and do your exchange that way. And it used to be that they do this with very high-speed CW. There's a link here how to use meteor scatter that's really good if you want to pursue that. Okay, here's just a picture of what's happening. You're shooting up, got an ionized trail that will bounce the signal down over here. That meteor might be gone, but another one will show up and let the other person come back to you. So the software keeps trying. Here's just another picture. It's a 6-meter array. And there's meteor showers that are predictable that happen in certain times of the year. So people who are into this would be very interested in this chart. Then Moonbounce, which I think is our last topic of the evening. That's where we're shooting up to the moon and then coming back down again. Used to be extremely difficult to do, but with software available today, it's actually becoming more accessible. So if both stations can see the moon, they can talk via EME. So here's our lunar orbit, and it's actually different one side versus the other. The perigee and apogee has to do with the distance that orbit is from the Earth. Perigee is the closest. The way that I remember this, because there's a pool question about it, perigee sounds a little bit like periscope, and for targeting periscopes on submarines, they actually magnify the image. So perigee, periscope makes the image look larger. Apogee and apart, I associate those words. That's the furthest away. So EME is not easy. So if we're running 1,000 watts here on Earth and we're transmitting it out, well, the beam angle is less than half a degree. If the moon was spherical, a perfect sphere, we wouldn't be able to bounce anything off it at all because we'd only have one point we could bounce off. But the moon is rough, and we're going to have a diagram of that coming up, which makes it possible. So it's a long, long way. It's much further than going around the Earth. Something called libration fading. It's kind of a rocking motion, and we've got the surface of the moon being very rough. So when we have an incoming wave front, it's going to bounce something back toward us that's much broader than just a single point hitting and probably not making it back. So the moon rocks relative to the Earth. It has an irregular surface, and these impact multipath, so we're getting more signal back. The effect is a rapid flutter. If you're trying to do it on sideband, I don't know if anybody does this on sideband. Deep fading in peaks, and then libration fading of an EME signal is characterized by a fluttery, irregular fading. And there's an article here, how to use Moonbounce, and then there's a wiki article on libration fading that you can look into if you care to. Digital modes have made this much easier. This is our friend Joe Taylor, and he invented, first one was JT65. That was originally meant for Moonbounce. That's been supplanted by Q65. It's another program within his software suite, and this is the one that's currently in use. Uses time sync transmissions, transmit for a certain period, receive for the same period. So stations have to be able to see the moon at the same time. So if it's 12,500 miles from one edge of the Earth to the other, that would be the maximum distance. So the approximate maximum separation measured along the surface of the Earth between two stations communicating by EME about 12,000 miles. I said 12,500, but call it the same thing. But the moon has to be visible by both stations. Now, there are a number of hams that have actually achieved their DXCC, 100 confirmed countries, via Moonbounce, and that's because the distances can be so great. So you have to have a low noise receiver set up. In the old days, people are using super cooled receiver preamplifiers and every bit of power and antenna gain that they could to even make it possible. But now the Q65 digital mode, because it is so sensitive, it's like FT8 or JT65, it makes it much easier to recover that weak signal. And back in the beginning, when JT65 was the mode used for Moonbounce, they wanted us to know something about JT65. JT65 has the ability to decode signals which are very low in signal-to-noise ratio, actually below the noise. Q65 is even better. So these are just different ways that they're asking pool questions. A method of establishing EME contacts is time synchronous transmissions alternately from each station, which is how Q65 works. It means you're transmitting for a certain number of seconds and receiving, and both of them have to be synchronized so they know where their time slots are. And libration fading is characterized by a fluttery, irregular fading. So a whole bunch of pool questions on EME. And if you're scheduling a contact, you have to be aware that the least path loss occurs when the moon is at perigee, or closest to the Earth. That gives about a 2 dB advantage. So 1, 2, 3, 5 pool questions, all on EME. And speaking of pool questions, we'll go over this part. I said it was a lot of small topics, so we'll go for it. How does the VHF-UHF radio horizon compare to the geographic horizon?
Alpha.
Alpha, approximately 15% further. What does the term ground gain mean? Some really funny answers here in the selection.
Delta?
It is delta, increase in signal strength from the ground reflections in the environment of the antenna. Which frequency band has the smallest first Fresnel zone?
Alpha.
Right, and my trick was pick the highest frequency because the Fresnel zone is smallest at smaller at higher frequencies. Atmospheric ducts capable of propagating microwave signals often form over what geographic feature? Charlie, large bodies of water. That's where you get temperature inversions. What is the typical range for tropospheric duct propagation of microwave signals? See if you remember this one.
Bravo.
It was Bravo, 100 miles to 300 miles. At what time of the year is sporadic E propagation most likely to occur?
Alpha.
Alpha, around the solstices, especially summer. At what time of day is sporadic E propagation most likely to occur?
Delta.
Between sunrise and sunset. That's when the sun is illuminating our side of the Earth. Where is transequatorial propagation most likely to occur? This
Alpha. Bravo, is it?
Well, it's alpha.
No,
Yep. Between points separated 2,000 to 3,000 miles over a path perpendicular of the geomagnetic equator, 2,000 miles north, 2,000 miles south. So it's about 5,000 total. Which is the next question. What is the approximate maximum range for using transequatorial propagation? That's Charlie, 5,000 miles. Me to Brazil. At what time of day is transequatorial propagation most likely to occur?
Charlie.
Afternoon or early evening, after the atmosphere is well warmed up. What is most likely to result in auroral propagation?
Charlie.
Charlie, yep, a lot of stuff coming in from the sun, severe geomagnetic storms. Which of these emission modes is best for auroral propagation?
Alpha.
Alpha.
Yep, because of its fluttery sound, single sideband can be difficult. Same with these other ones. So CW is why that's listed that way. Which of the following digital modes is designed for meteor scatter communications?
Bravo.
It is Bravo, the WSJT suite, MSK 144. When a meteor strikes the Earth's atmosphere, a linear ionized region is formed at what region of the ionosphere?
Alpha.
Alpha.
Yep, that's where E can help us again. We've got sporadic E happening, and we've got meteor scatter happening there. Which of the following frequency ranges is most suited for meteor scatter communications?
Charlie.
It is Charlie, and my clue there was think 6 meters. Fortunately, these don't overlap, so it makes it a little easier. Which of the following digital modes is designed for EME communications?
Delta.
Delta.
Delta, yeah, don't get alpha and delta mixed up there. What is the characteristic of the JT65 mode?
Bravo.
Bravo. Yep, decode signals with a very low signal to noise ratio, actually below the noise floor in some cases. Which of the following is a method for establishing EME contacts?
Alpha.
Alpha, right. Time synchronous transmissions alternating between stations. You talk, I talk. What is the approximate maximum separation measured along the surface of the Earth between two stations communicating by EME?
Delta.
It is delta. Yeah, the word visible might be a clue there if you don't remember. 12,000 miles if the moon is visible by both stations. What characterizes libration fading of an EME signal? Bravo. Fluttery, irregular fading, correct. When scheduling EME contacts, which of these conditions will generally result in the least path loss?
Alpha.
It is alpha when the moon is at perigee, when it's closest to you. And I've got a few quick bonus slides to share with you. The concept of antipodes, first of all, propagation related. So if you could tunnel straight through the Earth, where would you exit? So here we are in the eastern United States. You stick your head in the Earth, and if you go completely through the Earth, this is where you pop up. So it says here, oops, you're in water. Do you know how to swim? So here's a link that will let you try your location and see where the furthest part of the Earth is. So where could I make the longest distance contact? Well, it'd be close to Australia. So you might ask what country would be your furthest possible contact. That's how you could tell. The ionosound is a device. It's an upward firing radar that shoots up into the ionosphere, and what it does, the returns that come back from the device will, depending upon the height of these layers, will come back and actually show a picture. So this is how scientists can do that. So it's a tracking HF receiver. They shoot different frequencies and move up the RF spectrum and see what comes back. And of course, this wouldn't be legal on the ham bands, but this is how they can do radio science with these tools. There's some propagation and solar references that I wanted to share with you. Here to there, radio wave propagation. It's an ARRL book, which is excellent. Here's I think I had shown this a little bit earlier. These are some of the resources that you can use to learn a little bit more if you care to. This is a book that I picked up at Hamvention in 2018. The author was actually there and had a good chat with him. This is an excellent book if you want to dig into receiving antennas a little bit more. And that's all we had. Those were the bonus pieces that I had. So I think we've got about 3 minutes for class chat. Gary, if you wanted to take that. Or any comments from anybody, questions? And if not, we can talk about next week.
Thank you for your time.
Oh, you
Well,
bet.
thank you for hanging in there with us.
Yep.
And yeah, next week, the last chapter in the book, chapter 11, and I'm going to try to convince you that ham radio is not just a hobby, it's an adventure. So please stay tuned next week. That'll be the first half of class. And then for the second half of the class, we'll take a practice test together. 50 questions, straight from the ARRL website, and we'll see how we're doing. So please come back to us next week for Chapter 11, Safety, and a practice test. And then the following week, we'll have 2 practice tests, and that'll be the very last class. But you're invited to come back. We would appreciate you being with us.
Yep. Practice tests you can consider optional, especially if you already passed the test.
Yeah.
If
Well, if you
want-
pass the test,
Yeah. You don't need
you're done.
Yeah, you're done. Yep. So it's there for those that think they could benefit from it. All right. And if there's nothing else, we'll sign off for tonight.
All right. Thanks, y'all.
Yep.
Appreciate you. 73.
73 volts.
Yep.
Thank you.
All right.